In this chapter, we are going to look at common failure cases in BIM implementation. So far, we have talked about BIM as a construction best practice. BIM can improve coordination, reduce rework, support cost control, and help project teams make better decisions. But these benefits do not happen automatically. A project can purchase BIM software, create a detailed model, and still fail to generate real value. The key issue is whether the model is connected to clear project goals, reliable information, and daily work processes. This slide introduces three major failure patterns. The first is pseudo BIM, where BIM is treated as only a 3D model. The second is an ignored BEP, where a BIM execution plan exists but is not actually followed. The third is the field disconnect, where the model never reaches the site and therefore does not support construction activities. The main point is simple. BIM success depends on planning, accountability, collaboration, and actual use, not software alone. This slide shows the first failure pattern, pseudo BIM, or what is sometimes called lonely BIM. Pseudo BIM happens when a project has a 3D model, but the model does not function as an information-rich coordination and management tool. In many cases, designers and engineers continue working in isolated 2D files, and a 3D model is created late in the process mainly to satisfy a contract requirement. The model may look impressive, but it lacks reliable data. It may not include coordinated assemblies, accurate metadata, or useful links to schedule, cost, procurement, or field coordination tasks. In other words, the project has geometry, but it does not have a strong information process. That is why the diagram shows a progression from 2D silos to a late 3D model to missing information and finally to limited BIM uses. Without structured data and shared workflows, the model cannot effectively support 4D schedule simulation, 5D cost estimating, energy analysis, or model-based coordination. The consequences are serious. The team loses the opportunity for early coordination. Work may be duplicated. Metadata may be missing, collaboration becomes weak, and costs may increase. The lesson for construction managers is very important. A 3D model alone is not BIM. Real BIM requires integrated information, shared workflows, and collaboration from the beginning of the project. The second failure pattern occurs when a project has a BIM execution plan, or BEP, but the team does not actually follow it. A BEP should function as the project rulebook for BIM. It should define how BIM will be used, who is responsible for each task, what software will be used, how models will be exchanged, and what information is required at each phase. However, the BEP has value only when it guides actual project behavior. If it is treated as a static administrative document, it becomes disconnected from daily coordination, model exchanges, clash resolution meetings, and field communication. This slide shows several ways that this breakdown happens. First, the BEP may be copied from a previous project. It may sound professional, but it may not match the current project's scope, team structure, delivery method, software platforms, or trade participation needs. Second, roles may be unclear. For example, two trades may model the same component, while an important interface may be missed because everyone assumes someone else is responsible. Third, the level of development, or LOD, may be poorly defined. If the team overmodels, files become heavy and slow. If the team undermodels, the model may not support clash detection or constructability review. Finally, the BEP may not be updated as the project changes. New subcontractors join the project, design decisions evolve, and information exchange needs become more specific. If the BEP is not updated, it quickly becomes irrelevant. The lesson is that a BEP is not a one-time deliverable. It must be customized, followed, reviewed, and updated throughout the project. Otherwise, coordination can break down entirely. The third failure pattern is the field model disconnect. This happens when a detailed BIM model exists, but it stays in the office and never becomes part of actual site work. The model may be accurate and detailed, but it has limited value if superintendents, foremen, field engineers, and trade crews do not use it for installation, layout, quality control, issue tracking, or daily coordination. In this situation, field crews often continue relying on printed 2D drawings, email threads, separate RFI logs, and disconnected quality control checklists. These tools can still be useful, but they are usually less current and less spatially clear than a coordinated BIM model. The slide also highlights another important issue: as-built data is lost. During construction, field conditions often change. Equipment may be moved, access clearances may be adjusted, and actual installations may differ from the coordinated model. If these changes are not sent back to the BIM or VDC team, the final asset information model becomes inaccurate. This creates a low-trust handover resource. Facility managers need reliable information such as equipment locations, serial numbers, warranty dates, maintenance clearances, and as-built conditions. If that information is missing or incorrect, the model loses value after construction. The fix is not just to create a better model. The fix is to connect BIM to field workflows. BIM should support installation, layout, issue tracking, field verification, quality control, and final handover. It should not remain an office-only coordination tool. This case study shows how BIM can fail when digital governance and field adoption are not properly managed. In this project, a large commercial high-rise tower in the United States required BIM by contract. The building's mechanical, electrical, plumbing, and fire protection systems were complex, so the owner expected BIM to support spatial coordination and reduce field conflicts. The general contractor did not have strong in-house VDC expertise at the time, so the contractor hired a third-party BIM firm to create the model. That decision was not necessarily the problem. A third-party BIM firm can be very useful when its work is supported by a clear BEP, defined responsibilities, trade participation, and enforceable information exchange requirements. The project eventually had a complete federated model based on the designer's advanced drawings. The plan was to use that model for automated clash detection and coordination. However, the project had a major weakness. There was no customized and enforceable BEP. The digital responsibilities of the trade partners were not clearly defined. The contracts did not explain who had to model what, how the models would be used, or how trade partners were expected to participate in digital coordination. As a result, the MEPF subcontractors resisted the BIM process. They argued that their contracts did not clearly require 3D modeling for fabrication. They also said they did not have the staff, software, or technical capability to work within a federated model environment. Because the general contractor lacked a strong BEP and contractual authority to enforce BIM participation, the team accepted the resistance. The detailed 3D model was abandoned for spatial coordination, and the project returned to traditional 2D paper drawings and light table overlays. The consequences were significant. Hard and soft clashes were discovered later in the field, where they were much more expensive to fix. The lower floors essentially became a physical prototype. Instead of solving conflicts virtually, the team solved them through RFIs, rework, change orders, and schedule delays. The owner paid for BIM but received very little return on investment. The lesson from this case is clear. BIM success requires more than producing a digital model. It requires defined responsibilities, aligned contracts, trained participants, enforced digital workflows, and field adoption. Without those conditions, BIM can easily become an unused deliverable rather than a practical construction management tool.